Today we're going to be working on free body diagrams, and so I'm going to work through a series of these with you, and then I'll let you get started on them. So the first one, I'm going to do some simple ones, and the goal here is to understand the process of making them. So for this first one, we just have a scenario where there's a box sliding across a wax floor at a constant speed. The way that we're going to approach this is first by identifying the forces that are present, and then by drawing them in the diagram the way that they should be pointing. And so in this scenario, we'll go through the list. First, we know that it's in the presence of gravity because it's on Earth. So we're going to have a gravitational force. Okay. And then we also know that because it's touching a surface, it's touching the floor, there would be a normal force. And then now we have to think about forces pointing to the left and the right. So assuming that it's going to the right, we have to think if there's a force pushing it that way. So if we think about this, there's not a person, we could kind of go through our list. There's not a force of tension, there's nothing pulling it. There's not a spring pushing it. It doesn't have thrust, there's no motor attached to it, or engine. If we keep thinking, there's no, like an applied force, there's nobody touching it. So in the thing that we're doing today, sometimes you'll see applied force if there's a person pushing it. There's no applied force. And so nothing's pushing it forward. And then there's another clue here, and then it's going at a constant speed. Okay, so if there's nothing pushing it forward and it's going at a constant speed, that means there can't be any forces pushing back on it, otherwise it would be slowing down. And so all that we have in our diagram, we're going to draw a little dot for the box. All we have is our downward gravitational force, and then our upward normal force, and there's no other forces present here. And the clue here again is that there's a constant speed, which means, as we kind of discussed in class yesterday, all these forces have to be balanced. So these forces are balancing each other out, and the forces this way are balanced because nothing is pushing either way. So if there was a push this way, if there was a constant speed, then something would be pushing back this way. And then if there was friction acting on this box, it would be slowing down, or something would be having to push it in order for it to maintain that constant speed. Okay, in this scenario, we have a wagon being pulled at a constant speed. We're going to approach it the same way. So by identifying the forces that we know are present, so we know that it has gravity because it's near Earth. And we know that there's a normal force, and this is because it's touching a surface. Okay? Now, in addition to that, it says it's being pulled. That means there's a force pulling it to the side. So in this case, we'll probably call that, I'm going to say you could call it applied force, because like someone's applying a force. Or maybe you could call it tension. I'm good with either of those. I'll call it tension. And then finally the fourth one, now if we draw these out, if we have weight and normal force, and then tension. Now if this was the case, the wagon wouldn't be getting pulled at a constant speed. Okay, because the speed would be changing, right? This would be a wagon who has an increasing speed where it's accelerating. And so because it's not accelerating, that means that something is pulling back on it, slowing it down, and probably we'll say it's friction. And technically it's going to be static friction because it's rolling, but we'll just use general friction. Okay, and so there's our next free body diagram. So for our third one, we have a car again. We have a car this time that's getting pushed, and this time we see that it experiences acceleration. Okay, and so that tells us that the forces are not balanced. Anytime we have changing velocity, forces are unbalanced. And so we're going to take the same approach, and as I've been showing you this because you're going to be going through a series of free body diagrams, and I want you to take the same approach by recording what forces are present and then drawing the diagram. Okay, and so we'll go through our list. We know that there should be weight present because it's near Earth. Okay, we know that there should be a normal force because it's touching the ground. There's a surface there. Okay. And now there's a push, so we're going to call this an applied force. And then finally, probably there's some amount of friction between the car and the road. So we're going to say there's friction too. And so you'll see, just like the last one, we have 4 forces, but the difference is that this time the forces have different lengths. So down here we have gravity again, we have our normal force up here, right here we have our applied force, and the key is that if it's accelerating, the forces are unbalanced, so our applied force here is going to have to be longer than our frictional force, okay? And so we have something like this for this scenario. It's unbalanced. This force is stronger than that one, causing there to be a net force and causing there to be acceleration. Alright, I'm taking one more example here because sometimes I've noticed that students really want to just put as many forces as they can, and a lot of times there's just not a whole bunch of forces. So always start by, like when you're making your list of forces, only put a force down if you 100% can guarantee that it should be there based on the criteria that's in the book and in your notes. And one of those forces that students like to put a lot, whether it's present or not, is the normal force. So a reminder that normal force is only present if something is touching a surface. Okay, so in this, that's why I picked this example here, because this is an example of something that's not touching a surface, so it doesn't have a normal force. Now this has some different forces that we're not really using very often, and we'll talk about those. But just because we're talking about forces doesn't mean there has to be a normal force. This one we do use gravity again because it's in the presence of Earth's gravitational field. We also have, for this one, there's going to be air resistance or drag. Slowing it down. There's going to be a forward force that is thrust, we'll say. And then there's an upward force. The thing that lifts the airplane up is called lift. Okay, and it has to do with the way the airplane flies, the shape of the wings. There's an upward force on the wings based on the fact that it's moving quickly through the air, and that upward force is called lift. Okay, and then all these forces should be balanced. Here would be our diagram. We have lift, we have gravity, we have thrust pushing it forward, and drag pushing it backwards. I don't know if I said before that thrust is pushing backward. Thrust is which pushes it forward. And the way that the jet engine works is in a kind of an example of Newton's third law. So if you have an airplane going this way, it's pushing air out the back. And by Newton's third law, if you're pushing something out the back, then that thing is also pushing you forward. And so, like we said, for every force, there's an equal force in the opposite direction, and this is an example of that. So in a jet engine, there's a force backwards. It's pushing the air backwards, which means the air also pushes it forward. You get the same thing a similar thing when you like take a balloon that you have full of air, and instead of tying the end, you let go of it and it flies across the room. It's a similar concept where it's pushing back on the air, so the air pushes it forward. Okay, so I'm going to show you now the activity that you're going to be working on. So you're going to be working with this free body diagram interactive. You can click on this little button here to make the screen bigger, or you can click this to make it full screen. For the purpose of this recording, I'm just going to do this. I think when you're doing it, it's going to be easier if you go full screen. And so the way that you're going to do this is you press start, and it's going to give you a bunch of 12 situations, and you can go in order if you want. They're all kind of randomized, the sequence. And so what you'll do is, for each one, it's going to give you a scenario, and it's going to give you forces for each direction, right, left, down, and up. And in each case, you have the force, and you can, if you want to, for a couple of them, you might need to adjust the length of them so that some are longer than others. Okay, and then my advice here as you're doing this is that just because you want to put a force somewhere doesn't mean that you should. Okay, you want to not get force happy and put as many forces as you can. Just like we did before, you're going to make a list on your paper and then use that list to generate them. If you can only think of one force that should be present, only put one force. If you can think of just 2 that should be present, only put 2. When you're done, you click check, and it will tell you how you did. So this one I did incorrectly, so hopefully you'll do it better. If you have questions, send me an email. I'll reply to emails or school loop. I'm sitting at home with my daughter. She's sick today.